All right, so let's get into chapter 10, which is your unit 10. These are all your definitions, a heavy definition right here. Yeah, I am not going to read that for you because they're just objective. Of course, we're going to cover everything, yeah, everything written here one by one in our slides. So starting from here, the very first one. So we're going to get into profile. So when we look at the symbol, yeah, so this is your review. I ask you in test 2, yes. So your profile of a line is like that, and profile of a surface is like this. Even the profile of a line, you don't have to draw it like a little line. It is an arc, okay? An arc with a base is going to be your profile surface. So some students get it wrong, yeah? So make sure profile of a line is a little arc, and then your profile of a surface is the arc with a base, okay? So don't forget the base. It looks like a little, your angle measurement, yeah, device. All right, so I put a line right here for you. It's all messed up. So anyway, so here's the type of control is your profile and your geometric characteristic symbol, yeah? Okay, and then we will go into the points. Of course, not going to read this everything for you. Yeah, we will, as we go into the example, you're going to see very clearly, so don't even attempt to just read it one time and it should be okay. We're just trying to tell what the profile tolerance is. Of course, when you're profiling, we're looking at the surface, yeah, your contour surface. So that's what we'll be dealing with. And then, of course, it's got to be used with your datum reference, because without the datum references, you can't do any kind of measurement verification. Yeah, so that's how we measure. You need a datum reference to be able to measure, yeah, and check all these size, yeah, dimensions are going to be within the acceptable tolerance zone. Yeah, so that's also same is also true. Yeah, the same for your profile. It doesn't matter their orientation, location, or profile tolerances. We're gonna follow this about the same rule. Yeah, so repeating again and again. So profile tolerance, you're gonna always apply your RFS. So make sure when you study to take notes out of it, make it, you put it in your own notebook, and then trying to write it, compare it, so you know which one is regardless of feature size and which tolerances you don't need it, okay? Write it down one by one. So since you always, here is the point right there, always, yeah, apply to the regardless of feature size, you are not going to deal with your modifiers, yeah, so these little things. So if you gonna apply meaning using that tolerance, yeah, only for the feature size, regardless of feature size, you will always apply that. At that time, you are not going to use your modifier, yeah, may not be used. Of course, your bonus tolerance always, they are necessary for your modifiers. So right now, since you don't have the modifiers, you don't need the bonus tolerance. Yeah, so these are the major points that you have to know. The rule number 1. Yeah, most of the students have an issue with the rule number 1. I don't know why either. So rule number 1, again and again, I've been telling you like since the beginning of the semester, your feature size, your point controlled by any type of tolerance, that got to be fully contained within the.
Catch that.
Okay, here is your points. Yeah, so let's go back here for the profile tolerances. Anyway, so where were we? So we're doing the rule number 1. Yeah, so rule number 1, again, you have to know that you're dealing with the limits. All right. And that is going to be controlled by this profile tolerance. Again, remember your feature size, okay? And your important point is right here. It got to be fully contained within that limits, or limits of what? Limits of that tolerance, okay? So that is your rule number 1, the golden rule, yeah? And when you reproduce, you can write it in your own words, yeah? You don't have to write the technical term like this. Make sure you put it in your own words to make it easier for you to remember that. All right, so let's get into the basics. So your profile is when you think about your profiling, meaning like we're following the contour of the surface, yeah. So every time we build something, there are so many different surfaces that we're doing, not just a plain straight linear thing. We have contour, yeah, going up and down. So your derivative, yeah, your integration mathematically when you identify the surface or profile changes, yeah. So the profile is two-dimensional outline, okay, of your object or your feature in your given plane, okay. So that's we're looking at how the surface changes the direction. It's called profiling, yeah. So now take a look at in this simple diagram. And I told you so many times, yeah, the real life is you're gonna get a gazillion of those kind of parts, yeah, and you're gonna have so many different surfaces, contour. Not going to be easy like this. And when you add them up, here we go, your calculus, yeah. So anyway, so your profile view of your surface, and here is your second view, which is the side view of this part. So you have your surface A right here, and that's your surface A. This is your right side view. Looking at this, okay, so you can't really see that profile contour on the right side view, but you can be able to see it from the front view, so here is and go, your profile changes. See that how the direction of that line changes from here to this, orientation, right? Look at that, and going down like that. So your surface A is going to be identified in the right side view, and that's like projected in your front, frontal plane. And you can see the frontal plane, which is in this example is your profile view, because we can see the profile, different look at that, see contour right there, the first contour like that, second contour like this, okay. So it is your projection of the surface onto a two-dimensional plane, and we can see the outline of that surface profile, so that's your basic concept. So the profile is again your 2D outline. This is very important of your object or the feature on a given plane, okay. Now what is a given plane? So we're going to go back to one slide up. This is your given plane because you can't see that surface A of the right side on the right side. You can see the surface A of the right side view on the frontal view, and that frontal plane, okay, is your given plane because we can see the outline of it, yeah. So now you have your precise or your perfect profile for your geometric shape, and we're going to refer that to the true profile. So if you have a true position, we call it true position, true size, true angle. Now here, true profile, yeah. So the true profile got to be defined by using the basic, everything that is true is with your basic dimension, by the way. We know it, and I've been telling you again and again every chapter. Yeah, so basic dimension is for your true stuff, so true profile. And of course, you're going to formulate that to get your geometric definition, absolute geometric definition. Absolute cannot happen in real life, therefore, the accuracy can never be 100%, because we make error, every time. Because everything that we do for the true size doesn't have a body. So when you have a body in the physical world, you got that body. So in the document or paper world, you don't have that body, right? So when you do the machining, you will be losing some of the material, So therefore, yes, it can never be absolute. It can never be the true size of it ever, even for the outline of your surface, your profile cannot be absolute, the same thing, we can make it the best, but we can make it as it is defined in the true profile in this case, all right. So let's get into the what is this basic concept continue. So let's take a look at it with the dimension. All right, so dimensions, you can pinpoint it right there, 13, 12. We have, your radius. Why? Because you're dealing with the arc, the arc of your first circle. The second, one is right here, so we have two radii right there. So the first radius is 18, and the second radius is 18. And the size of that from here to here is 13. And you can, of course, loosely vary between 13 and 12 for this, for that part. And on the right side, we can be able to see the side, the side of this part. This is your front view. So the right side view is going to give you the depth of that part. So that's a 16, vary all the way to 15.4. You can get your basic size right there. So the basic coordinate radii, the basic radii, basic coordinate dimension, basic side dimension, okay, are drawn right here in this example. Okay, I don't remember if I covered this or not. So let's take a look at. So, anyways, your precise or perfect profile cannot happen, because your basic dimension is going to refer to your two-dimensional outline of your profile, which is your profile is your two-dimensional outline of your object. So the true profile got to be defined by using your basic dimension. And then in this example, we have a two radii right there. One of them is this, and one of them is that. And then this is your height, and this, of course, your depth of that. These are all the true, true profile basic dimension. Because a true profile must be the basic dimension, and it's got to be applied to the view that you can see the outline of that profile. All right. So anyways, this reiteration of that. So we will jump this two and then go into the profile tolerance. So tolerance again is a zone, so therefore you have upper and the lower limit, which is linked to the size upper and lower limit of the size of the feature. Then we are looking at only the outline of the surface, so your profile tolerance is your boundaries, of course, where you can do your errors, in manufacturing processes. Okay, so your boundaries, of course, all of your elements on your specific line. This is very formally defining the profile tolerance, meaning like the outline got to be in that range. Again, if you simplify it, so all elements of a specific line or all elements of the entire surface got to be in that tolerance zone, which is your boundaries. It's writing it very formally. That's all. I want you to don't get into formal definitions. I want you to change it into your own word and write it in the way you speak it, please. So these boundaries you can equally or unequally dispose or entirely offset on one side of the true profile. So don't worry about it. I'll show you in the example so you can see it better. So let's go into there, and we have our, of course, this is your outline, and that's our plane, surface plane that you can see this outline. You can see, all right, this profile on the right side view. So now we'll get into this, the 18 and 18 right there, 13 and 12 doesn't change. And here's our data, because here's your control frame telling you this profile tolerance has got to be in this 0.4. So this the profile changes got to be in that boundary. So you know the boundaries. We know that this is a profile tolerance because of this. See, look at that symbol. Yes. If you don't have the base, it's going to go to the line. Okay, so the profile tolerance zone is implied, and that's going to be equal bilateral distribution of both sides of your true profile. And then your total tolerance is about 0.4 millimeter. And of course, another thing that's given to you is 0. Let's say you can offset it to 0.2. Yeah, I was right. Okay, so here, 0.2 millimeter on each side, because the total is 0.4. So let's take a look at how we do that. So your ISO is another standard body. So international standard organization. So you're gonna have that tolerance zone. If you follow this standard body, you're gonna get your tolerance zone as your two boundaries, which is drawn right here in this diagram like that with this little, look at that yellow lines right there. So these are all uniformly or bilaterally. Bilateral meaning on this side and on that side of that surface profile. So distributed about the true profile. So your true profile is your white line, and your zone is your yellow line right there. And your little circle right there is going to show you your 0.4, which is this profile tolerance right there, controlled by or measured from your datum B and then your datum A right there. You can see the datum B surface and the datum A surface in the same view, because that's a right side view and that's a front view. So I want you to review MET 101 and then practice to be able to understand these views. So if you don't study, your other course, which is your engineering drawing course, then you're gonna have an issue trying to train your eye to be able to see this view very quickly and spot it. So your height and your height and your width and your length got to be in your head. Doesn't matter which view you're gonna see. So every 3D object in the space that we know as far as existing in this in this world that we know in our nervous system. Okay, so that has only 3 dimensions. That is your depth, your width, and then your length. Okay, all of the body's object is identified in that dimension. That's all. Time doesn't exist. Time is just a measurement. Okay, so we're just looking at the things that we know, and we're looking at that and between a 2 reference point, the time that we know. So if you think about the calendar, right, time, calendar is not your age, by the way. Calendar is just a calendar based on the movement of your planet. Okay, your planet, and our reference is your sun, which is your solar system. Okay, so that's just going with 365 days. So then we count for human age, that's a year, right? A year older, like that every time. But then that's just a reference. The thing is, like, everything is happening here that we know, and that is happening, and our reference point are location, by the way. Okay, so you're looking at the location and how that is moving. So don't forget these things. So when we do the measurement again, we're dealing with the dimension, 3 dimension only for everything that we measure, for the size of anything in the objects. That's because you don't have that reference point to measure the time, because it's just a drawing here. So therefore, you only have to deal with that 3, dimensions right in there. So when you're gonna deal with the bodies, a physical body outside, the bodies are like doing any kind of movement in the space. So when it comes to this, so you gotta look at where is it going from where to where. So if that's going from point A to point B, how long does it take going from here to here to do the activity? So there it came your time factor, the full measurement. But then that's just a measurement, because your watch or your digital clock or that's just counting, counting in unit, by looking at something is either doing an activity. Usually is motion, by the way, all the time motion, because you becoming older and older every day is a motion of your everything in your body, the motion of your body, and so trying to please a review, or other science foundation that even though we're doing the basic concept, because it's related to engineering. So everything that you draw got to be thrown into machining for manufacturing, and people are using the functionality of the parts that you're drawing and being manufactured. So anyway, so let's go back to here, and we will be dealing only with the 3 dimension, which is your width, and then your length, and then your height. Okay, so let's go into there, and now we see the little zone right there for your surface, which is your profile right here, and we have 2 different arc right there. The first arc with first radius, and the second arc with your second radius. So you can see this boundary limit is identified in your control frame right there, 0.4. Your datum A is here on this view, and then your datum B right there. We're going to gauge it. So gauge it means bring a surface gauge and then stick it to the surface, and I'm touching all the high points right there, so we can identify that plane. You have already done it 1,000 times, so you know what that is. So just trying to verify these tolerance zones are reasonable and accepted. So okay, so anyway, so let's get into the next. Oh, I think I forgot to tell you. Yes, so here anyway, so this is just a different view that you're looking at this. So we can be able to see right here, there's a little zone. See that? So that's your surface right here. We're looking at this way, by the way. Yes. So we can see around here and around there. So don't forget, that's a front view and that's a right view. Even though we're seeing the same zone, the view of the zone is different. This is from the front, and this zone is from the right side, seeing this little hole right there. Okay, so let's get into the next one. Now we're gonna get into this little arc right there, concentrating only that part, and that's a 0.1. your control frame doesn't change with your datum. Reference is A. Yeah, so primary datum, 3 touch point with a gauge. So here is your surface or profile. And so in this case, your tolerance is unequally, right, disposed about that true profile. Your true profile is this white line right there. So the total range of the acceptability, which is defined here in your control frame, is 0.4. Yeah, so you can see that, and you can see that unequal disposition is because of the additional dimension. Yeah, because you have additional dimension 0.1 right there. So it's just showing you the boundary can offset, and that boundary offset on one side. Yeah, so when you look at it, pay careful attention. See that how the zone is shifted to very, yeah, the lower part is closer, look at that, to this white line right there, yeah, which is your true profile right in there. So that is what we're you can be able to see the unequal disposition on each side. Yeah, they're not equally distributed like here. Yeah, okay, so let's go down. So we draw, of course, the yellow line with your phantom line. Yeah, so your phantom line is going to extend only as far as it is necessary to give you that tolerance relationship with your true profile. Yeah, so we're not drawing the phantom line, the entire profile outline here, but we only draw it here because that tolerance apply only that area right there. Okay, so that's what it's saying by implication. Your undimensional site contains a balance of your tolerance zone, and the phantom line extend only as far as necessary to convey the tolerance relationship to the true profile, only in that zone. Yeah, all right. You will see, if you see that kind of dimensioning like that and tolerancing like that, you know what to do. Okay, and if you get the specification sheet, you should be able to draw that in your drawing in that way. Okay. Alright, so now the bilateral tolerance, so unequally disposed about the true profile right there. And of course, right here, you're going to have like a 0.3. Right there is a 0.1, yeah? So it's not the same, the outline, okay? And then we'll get into the next section, which is your unilateral, okay? Let's go back here. Did I forget to show you some? Oh yeah, we're okay with that. Here is, we'll get into our unilateral. Unilateral meaning like instead of see like both lines for the tolerance, we've got only one on this side. Yeah, so we'll be like concentrating unilateral tolerance, meaning that the entire tolerance zone position only on one side of your true profile. So here is the white line as your true profile, and you can see the little yellow line right at the arc right there, yeah, with our control frame, and that is your unilateral tolerance, meaning this is not going to give you the zone on each side. It's going to give you the zone on only one side of that surface, yeah, which is this profile, of course. And of course, your true profile is going to be located with reference to that datum, yeah. So we always have your leader line, yeah. From that feature control frame is going to point to the phantom line. Don't put your leader line on here, white line. You gotta stick it, to the phantom line, the yellow line, because we want to point out, hey, this is only unilateral tolerance. And then of course we're going to go into the entire surface. So when it comes to the entire surface, we're dealing with all the line elements on that surface. So it's got to be within, again, the same thing in the same tolerance zone, and it's got to be parallel to your data. So instead of, even though we're doing the unilateral, this is only that chunk, and here is, we're going to go into the entire surface. So the profile tolerance zone is again limited on one side of the true profile, and that will be controlled by your basic dimension. So that's a uniform boundary unilaterally offset above the true profile, and it's going to be limited on the outside of a profile, about, in this case, 0.4 larger than the true profile. Alright, then we're going to move to the other side. So the phantom line is going to show you the tolerance zone, which is going to be offset from the true profile on inside of that object. So here is your part, and this is your body of the part, and you can see the phantom line inside of that part. So now it is below, of course, your profile surface. which is going to be located again from your datum reference A. So now we're going to see the entire, so all elements are going to be on that line tolerance zone. Okay, so let's get into the entire surface. So when we say the entire surface, all the elements along that is going to be within this tolerance zone. So your profile tolerance zone is going to be limited on the outside, all right, by your true profile, because your true profile line is not outside of this tolerance line. See that? Of course, it's going to be limited in this case 0.4 because it said so here in your diagram. So that profile uniformly is a 0.4 smaller, meaning like because it is inside, so it is smaller. If this line is outside, it is bigger than your true profile. Again, you can be able to see it with your naked eye because this variation, even though we draw it really exaggerated on the paper, is very small, is a very small, right? A thing outside on the real part. So you can't be able to determine by using your eye at all. You have to use a measurement tool to be able to spot those kind of error. Okay, so let's go down. So we're gonna go to the basic concept. We're gonna review the first section of your profile, and the profile is again two-dimensional outline of your object or the feature is going to be projected on a given plane. This is very important because you can see that profile in every view. Okay, it's got to be a particular plane. So make sure you spot that first, and then of course you have your precise and perfect profile, and that's going to be called as a true profile. And your true profile got to be defined using only your basic dimensions, okay, to establish your absolute or the true geometric definition. And then your your profile tolerance have boundaries, and these boundaries again are going to be where your lines, your elements got to be in that boundary. Okay, so your rule number 1. So these boundaries may be equally or unequally disposed. Sometimes they are entirely offset on one side of the true profile. We have already seen 3 different examples. So if your tolerance zone is not specifically designated, then you gotta understand that that's a bilateral. But if you have the other way around, it's going to be a unilateral. So right now, let's just concentrate in bilateral stuff. So where you have an equal distribution of the tolerance on both sides of your true profile. So when your true profile of the line is used to control the form, the variation of the control feature approaches the limits of the tolerance zone boundaries. So again, don't worry about it. Let's go and make sure that you understand everything that I have covered. All of the points along the profile, your tolerance going to apply perpendicular to your true profile, and then your compliance got to be verified. And how are you going to do it? By maintaining the actual measurements, normal, meaning like 90 degrees to the surface in when you're doing your inspection, or by projecting the 2D image of the outline onto the target template. And sometimes, of course, you use the optical comparator to do that job. Okay, so let's go into the next section. Okay, inspection. So how are we going to inspect the profile tolerance? Mean like verifying that. So we can inspect the profile tolerance by using a gauge. So this gauge is a measurement tool, also a verification tool. So you're going to use that, and then what are we doing? We are going to gauge it and find the perpendicular, perpendicularity, test the perpendicularity, and it's going to be perpendicular to the control surface. So your control surface, is going to be in that range. The surface is within this limit, which is defined right here in your control frame. So that's your specified tolerance. So this is what we measure, So by measuring, we can verify or inspect that surface, which is your profile here, So here, in this case, we're dealing with the bilateral tolerance zone, And that is, again, a 0.4 anyway. So you have your true profile, your white line, and then your actual profile is your blue line, yeah? So the actual is a little bit offset from your true profile in this example, and we're gauging it. So if I say I am gauging something, meaning like in the lab you're using a tool, and which is called a gauge, and we are verifying that surface, right, is within the accepted tolerance zone. All right, let's go into the recap here. Okay, so recap of your profile tolerances. So your recap is on your profile tolerances, everything we have covered. So you have your uniform equal and also your uniform unequal, yeah? And we did the bilateral and we did the unilateral tolerances. We know where they are. Yeah, unilateral has a two side, this side and that side, because your profile has two sides, yeah? First we go with the equal distance, the other one is unproportional, yeah? Okay, so your profile tolerance, again, this is very important, so it is highlighted right here with yellow. So your profile tolerance always apply regardless of feature size, don't forget that, yeah? So if your control is imposed as your refinement of the sites, this is just a big word right there. Just make sure that every time we do the RFS, yeah, we don't have the modifiers. So that's all you have to understand. And rule number one is your stuff got to be fit, yeah, right into that limits. That's it, yeah. At least you got to get that. Okay, profile tolerances. Sometimes they may or may not be established with your datum reference, meaning like relative to that datum references. And that's because they will control the form, or they have like a related geometric characteristic, dealing with that. So sometimes you don't have to use a datum reference. Okay, so that's what's the same right here. So geometric characteristic like your size, your orientation, location, we can use it to deal with the profile tolerances. Okay, then we will go into the line. So profile of a line. So now we don't have a base right there. Yeah, no base right here, just the arc. So controlling form with profile tolerances. Okay, so tolerance zone for the profile of a line. So now we're going to look at the individual line elements. Yeah, of course we're still in the two-dimensional space. So we will establish that by using two parallel lines, yeah, because it is a line, so you need two parallel lines as a zone. So you will think about the offset and equal or unequal, yeah, bilateral or unilateral, by using that two parallel lines to study the profile, line profile, yeah. So the tolerance zone is going to define the extent or boundaries. Okay, so when you're dealing with your tolerance zone, you know that that's going to extend the entire length of your true profile, yeah. Even though we're dealing with the profile of a line, so that's pretty much the same, yeah, as your regular profile. So when you verify the feature profile requirement as an inspection or verification purposes, your tolerance zone is going to apply independently, yeah, to each line element. So you have infinite possibilities for verification. So let's take a look at it. So we have here my arc, yeah. So we have that arc radius is going to be 12. So you're going to put your little line right there, showing that's going to be 12 for your radius, and your look at that line profile is going to be 0.2. Yeah, instead of calling profile of the line, I'm just going to call line profile, yeah, to make it easier. So of course we have a control frame right there. So you gotta make sure that you're gonna stay in that tolerance zone, which is 0.2 for that line. Yeah. Of course, that zone is going to be identified with the two lines. Let's get into the yellow. Yeah. So that's your two lines to identify this 0.2 zone right there. Yeah. So 0.1 on this side and 0.1 on that side. So that's your bilateral. Of course, your profile tolerance boundaries, yeah, you can see this on both views in this example. Okay, so the location of that line profile, yes, is going to be determined by your tolerance dimension right there. So the profile tolerance is in this case, yeah, bilateral. Bilateral means equally distributed. So if you have like a 0.2 total zone, since you have like a two, your line is in between them, we can distribute a 0.1 each. Yeah. You'll provide tolerance for each line element. Is going to control that form, yeah, which is your profile, line profile. Profiling is just a form, like how it is shaped, yeah. And here is, you are seeing the right side view of this, yeah. So you can see here, see that zone right there, and then of course this one. These little blue lines are just showing you your independent, yeah. We said, oh, there's an infinite possibility in the previous slide, and just showing you the independent verification checks that you are checking, yeah, probing to see that float within that size tolerance. So it's just around here. So you're going like check, check, check. Yeah, it's just a different view, front view, and then this is your right side view. It's a little bit difficult, yeah, for you to be able to see it. But then it's the same zone anyway, yeah. Okay. So you don't have datum control for location. So the boundaries like established by these lines, yeah, equally spaced. Your true profile is right there, the white one, and it's going to control the individual line elements. Okay. All right. So now let's go back here. Go down there, and we have a exaggerated, yeah, diagram here showing the imperfection on your right here profile right there. I'm going to put that in the zone. Yeah. So our dimension, so from here to this green line is 18, and the top is going to be 19. Okay, so this you can subtract it, and that's your you have 1.4, yeah, difference in between them. So anyway, so every time you do the tolerance check, your line profile got to be within the boundaries, yeah, and that boundaries is determined right here in the feature control frame, which is your profile control, which is 0.2. And in that case, we will accept that, yeah. Okay, so now let's go into the exaggerated. So here you can see, yeah, the green lines, and then I'm going to show you the location limit for that true profile. So the yellow lines right there, yeah, see that? Don't forget the view, all right? This is the right side view, which is this one, so don't confuse with that. I'm going to come back here. So this is the right side view, right? And here is your checkpoints right there, the little blue lines, your individual line traces, you know, with the gauge that you are verifying. So you can see the heavy, you know, blue lines. I'm going to show you the full range of the variation. So you can see the variation of the profiles, because see that is going up and down in our exaggerated diagram. So we are tracking, you know, that variation at each point represented with this thick blue line right there. Yeah, so you can see how it is different from your yellow lines, which is this one representing the limits of the accepted tolerance zone. Okay, again, these little things are, when you draw it in the front, is this. When you look at it, it's just showing you only here. Yeah, it's a little bit difficult, maybe very difficult, I don't know, for you to be able to switch the view, yeah, and make sure you draw it, yeah, draw it by application or draw it by hand to see that point, why it isn't continuous and why it is vertical. It is vertical because you are looking at it, yeah, from the side. Okay, so now let's go into the next slide, and you can see the zone, your tolerance zone, yeah, where you can see the control of that surface line is completely floating freely. So you can see that little yellow, and then see this little green one there, and then your true, yeah, profile line is right there. So you're in the larger location tolerance, and because no location reference, data, you don't have the data reference right there, we can just use, right, this tolerance to control that profile line, okay? Meaning like this tolerance zone, okay, can float, meaning like you can rotate, okay, for this example, for this part. Of course, we are going to accept this part, yeah, and pass the inspection, and that's because your surface, your control surface, is still within the zone, within the location, right, tolerance zone. Even though you're dealing with the profile, it is still in the location tolerance zone. Since we're using the Zeiss form and location tolerances, you do not need the datum, yeah, datum reference to measure the profile tolerance. Okay, then we come into our review. So the review is going to be your true profile got to be defined by using the basic dimension. So that's your mathematical formula, yeah? We have already seen that. The most important thing is right here, which is your profile tolerance are always applied regardless of feature size, yeah? So therefore you don't need the modifiers. If you get that, I'll be very happy. And so no modifier, we're going to use it, yeah, in your feature control frame. You don't need the bonus tolerance because there's no modifier, yeah, so you don't have to worry about the bonus, so that's good. And your tolerance zone is comprised of the two little lines, yeah, I've already showed you so many times, equally and unequally offset. So you have bilateral or, yeah, unilateral offset. So now let's get into the second example with this part, and you have a two profile line right there. So your datum C and then datum D, okay? Now we're not going to use a form or location tolerances to control that. So since we're not using these, yeah, external control, we'll have to use our datum reference to control this two profile lines right there. So your profile tolerance is bilateral in this, so they will equally distribute away from that true profile line. And here is our radius, yeah, radius for this, radius for that, radius for this. And we have a two control frame. One is 0.08 for that, and the other one is 0.04 for this. Okay? And of course, we're sharing the same datum reference, which is your D right here on this view and C right here on the side view. Your side depth is 16 to 15.4. Now we're going to gauge it. So put the gauge, do a touch point. Your C is a primary, so 3 touch point. Your D is a secondary, so you have a 2 touch point to the highest point, yeah? So we can be able to see the datum plane right there and right here. And they are, of course, review 90 degree, yeah, to the surface. So uniform offset line, we can see it right here, and there's a yellow zone right there, yeah? So all you have to do is divide that with 2. So if you have like a 0.08, you're going to get 0.04 on each side, okay? Then of course, we're going to go into the profile. It's going to be located, yeah, in the tolerance dimension right here and right here. And then we're going to segment it by using this, right, dimension. So that's a 12, and that's a 12.4, and so this distance is going to be 0.4. And again, you can free float, okay, free float within the larger location tolerance. Okay, so now let's go down to look at the side view, which is, we'll come into our, let's see, there's a little surface right, the exaggerated surface of this. So your tolerance verification, again, the checkpoints, yeah, they are all independent. So each one of that checkpoint is going to tell you your float, yeah, allow your float within the larger tolerance. Larger tolerance meaning you're comparing that, yeah, see this one is a larger tolerance. And then of course all lines on that surface, all right, it got to be oriented within your specified tolerance, which is relative to that datum plane, which is your C right here, okay? Okay, so your true profile is right here in the little white line. Okay, so that's got to originate from that datum plane, which is on this side. Okay, you can't see it from the front view. You have to look at it, yeah, from the side to see the surface. And I think that's the hardest thing, you know, for you to be able to do it, the switch of the front view to the right side view, and at the same time looking at the profile line. And then this is what we're measuring, yeah, the tolerance at this side and then that side, which is going to be here, is that, yeah. And you have top, which is this, lower is this. Do not think that is this, it isn't, okay? We're looking at the side, so the side is going to go to the back, okay, to the back of the this object. And I think that's the hardest for you, so that's we're looking at the side of that, the first front profile, yeah. Okay, so here are checkpoints right there. So for verification, so your green line is going to represent the profile locating tolerance, and your profile is going to float in that zone, okay? Don't forget the change of the view from the front to the right, and you know that this is a depth, right, going in towards the back. And your yellow lines, heavy ones right there, is going to give you the range of your profile tolerance, yeah, specifying that control frame, which is back here, yeah. Okay, then we're going to put this little, see that little red lines right there, and that's going to superimpose on your exaggerated view right here, yeah. So it's going to represent your maximum variation, meaning like it's going to go away from this accepted, all right, value right there. So see your max variation. So that's going to exist along that each independent line element. Yeah, check. So we check here, 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 here by using the tool, okay, measurement tool to check your inspection, which is usually a gauge of something. Okay, now we're going to use a gauge measurement here. We're going to put right here, here, here. Of course, that's just showing you 3 point here, but you will be checking, yeah, many different points independently, so you can see them. So the red line is going to represent the actual surface, yeah, for your inspection, and your white line is your true profile, and then the yellow line is showing you the zone, yeah, based on that tolerance value. Okay, so let's summarize it. So your basic dimension going to give you your actual true profile always. You know, every time you got your basic dimension, you got your true profile. So if you don't have your datums, then we will be using a location dimension. Yeah, they got to be non-basic, and your profile tolerance again are always applied to again. Yeah, regardless of features. I pointed this out several times. Your tolerance zone is going to define by 2 parallel lines. Sometimes they're equally distributed, sometimes they're unequally distributed, yeah? Your bilateral and your unilateral. And then your profile line, again, is going to be applied with your datum reference, your form, your orientation, okay? They can be controlled. Okay, so we will go into our decision making flowchart right there. So first we're going to look at the control applied to the surface line element, and if that is yes, we're going to see if that's applied in appropriate view. Yeah, view is very important. You remember that we switch from the front and also to the right. Yeah, and that control surface line is shown in the true profile. If that's yes, then we're going to look at the true profile defined by using the basic dimension or not. If we use the basic dimension, we're going to look at the modifiers. If we don't have the modifiers, your tolerance, we're going to check if that's in that's of your location dimension. If that is the case, then you're going to accept that, okay? Okay, so we go over again. Control, yeah, apply surface. This is just a previous slide. I was taking a break and come back. So you go to the true profile. I don't know if did I leave it here? I don't remember. Okay, whatever. We can restart it again. The summary. So we see our application guide. Yeah. So we do the same thing. Start with your surface line element if you have it. Then you go and look at your contour surface line if it's a true profile. Then we look at the true profile defined by using the basic dimension or not, because you need the basic dimension to do your true profile. Then we look at the modifier. You don't need it. Yeah, if you don't have it, we will look at the geometric tolerance if we use your location dimension. Yeah, meaning like you just change a little bit on that location dimension to control the profile tolerance. Yeah, then it is acceptable. Unacceptable, we look at it, and if you don't have your surface line element, if that control isn't applied to it, then it's unacceptable. And we look at the applied inappropriate view or not, because your profile tolerance got to be specific in view where your true profile of that line or surface can be seen, okay, clearly or displayed. So that is going to be unacceptable. Of course, then we'll take a look at your true profile define using a basic dimension or not, because basic dimensions are always used to define the true profile of the feature, being controlled. Then we look at the modifiers. You don't need it. So if you have it, then it's unacceptable, because profile is always applied regardless of your feature size. Okay. Then I will take a look at if you use your location dimension to refine your geometric tolerance, to control the line profile. So these are what we do for our decision if the application of that tolerance for that line profile is acceptable or not. So then we'll get into the application exercise, problem number 78 in your textbook. Yeah, and here is the answer. So make sure you don't copy it. Make sure you study with it, okay? It's just reiterating everything that I have covered so far. And then exercise number 79 here, your number 80. So your test question, yes. So this is your final portion of it. Will come from these exercises that I show you, just like that, yeah. So by that time, I believe that you have already studied, okay. So your profile tolerances, date, time, shift, they're always applied to RFS, and you can't modify. Yeah, you can be modified. So your profile of your surface is the next thing that we will be getting into. So don't forget your symbol has a base, back on. It isn't line anymore. It is not a surface. So we'll go into profile with your RF, related feature tolerance. Don't worry about this. This is just so bulky. We will get into it one by one. This is mostly reiterating the same thing. We have seen this again and again. So let's get into the first example right here. And we have a part right there, and we have X and Y, and your R, define your feature control frame is right there with 0.6, okay? And we can be able to see how, look at the X is changed into an arc and then go back into Y, that's what it's showing you right there. Then we're going to switch view so you can see the depth of that that part, okay? Your tolerance zone again is your three-dimensional thing, and you have your entire surface that's going to be controlled between your X point and the Y point, and we have a bilateral zone. So I don't have to repeat this again and again, so I'm going to go a little bit faster, So we're going to pinpoint your R, your profile, surface, your control, tolerance, your datum, which is going to be seen on your right side view. Don't forget, you got to switch your view, right, in and out. And unilateral, we're going to go only one side, okay? It can be on external side or internal side. We will cover both of them. Your datum is still A. That's what you're going to measure for. Then you can see the second one is in the inside of the part, I don't have to repeat that again. You should be able to pinpoint these things very quickly, okay? So now we're going to throw in our dimensions right there. And now we have a 2, okay? 2 frame right there. The very first one is on this side, the other one is right here. Okay, that's your two surfaces. Okay, from here it's a little bit difficult for you to be able to see it, but then here we are showing you, because that's your planar surfaces that form the base of that part. Okay, and that is being controlled as a single, right, surface. But then you actually have two surfaces, by the way. So make sure you review your MET 101 to be able to see these views. If you're not mastering the engineering drawing, it will be very difficult for you to appoint these projections or your views. So the next slides will go into the datum sequencing. So here we're going to do the datum sequencing. So we have a datum B and A here. So your elements on that surface point from X to Y, right, got to be within that profile tolerance point 2, in this control frame showing you A, B, C. So you have your B and your A is right here, that you can be able to see. Your datum C is right down there for the two surfaces right here at that feature. So you see they're located or positioned with a reference to your datum B and then your datum C, where they're right angle to each other between that two surfaces. Okay. Let's start sequencing. So, wait a minute. So make sure you understand, the location of that, because all of the elements on the surface, right, oriented on these datums. One is a datum A. We can see the perpendicularity of that, and then your datum B and C, that is positioned with reference to that. Meaning like this perpendicularity is reference to this surface and also that surface. Because if you extend it, it will go to here. Don't forget the change of the view. Okay, that's the side view, and this is your front view. So that's why when you write the datum A is right here, it can be seen like that in the back. And this one also, of course, is right here. All right, and then we'll get into the next one. Your next one is profile tolerance. You're gonna see as a control for your multiple surface polygons. So here, see that we're now dealing with the polygons, and relative to your reference data. So that's in this case is a nut. So the Auburn nut is shown right here, and they have, of course, your polygon surfaces right there. You can, of course, purchase all of that part. So we have our axis, thread right there, and everything got to perfectly coordinate to each other with these nut surfaces. So here we are, and this is the control frame for this, all right, profile right there. Of course, the angle between this profile and that is going to be 60 degree. Your datum is right there, which is your datum A, the primary. So the touch point, three points in contact. And then, of course, your diameter, you have a value for that diameter, for this. So just talking about this part, because it's got to be the design. You can't get it off the shelf, right? When you go to get the parts like Lowe's or Home Depot or Tractor's supply store and things like that, etc., etc. So this type of nut you need to design locally, So the hexagon hat. Okay, so right here, your Auburn nut, it will be controlled with your profile of the surface tolerance like this. Okay, so that's what it's been talking about. So don't worry about it too much. If you can be able to read, the frame, I'll be very happy about it. And then if you can be able to pinpoint, if I give you this, and that gotta go into this box, and of course, even though we show only one surface, that you're dealing with the polygon surfaces, so you will count all of it. So 1, 2, 3, 4, 5, 6. Okay, so this indication right there, for that control frame. All right, and then of course we get into the tolerance zone, showing you the true profile right there. And then, of course, it is a bilateral, so you see the equally distributed on each side of that true profile. Your tolerance zone here, identified. So you have all 6 surfaces are being controlled with this datum A, okay? Your true profile, when part mounted on the datum axis A, right, they mounted like that, straight in, yeah? Your axis is right here, the center axis. Your data is shown right here in this view, yeah? And that's your 0.4 tolerance zone, clearly shown to you with yellow lines. And then of course, you can vary, yeah, in between that zone. So here, this, see that? That's your tolerance zone, 0.4. And then this red line right there is going to show you your orientation, yeah, how the direction changes between that sides when the part is going to be mounted right here like that. Okay, so anyway, I think you can be able to see, yeah. So when we go back into the profile review, we know that your profile is going to be applied to any type of your part feature, your basic dimension, yeah. It's going to deal with your true profile. You're going to locate your dimension, yeah, but your basic dimension or standard coordinate dimensions, yeah, maybe your location dimension. So since you're dealing with the profile tolerance zone, that got to be either bilateral or unilateral. These are the same thing again and again, telling you with a different example. So your feature true profile is a perfect two-dimensional, again 2D projection or outline of that feature, yeah. Again, your feature can be seen on a plane, okay. So when you define your true profile, you have to have your basic dimension, because without that, it's impossible to have your true profile, yeah. All right, profile control, and we are going to deal with the code, yeah, planetary, planarity. Oh my gosh. So that means that we're sharing the plane. So here we go. So controlling the coplanarity with your profile tolerances is a condition where you have like a 2 or more, right, non-continuous surfaces, and they have elements. Of course, every time you have surfaces are composed with elements, yeah, and sometimes, of course, they can be on the same plane. So the 2 parts shown right here, yeah, in this example, of course, you have a non-continuous plane, because they're not continuous, meaning like you're gonna have like they can be controlled with a single plane, okay. So you can see it right here very clearly. So we'll get into the frame right there, yeah. So your frame is here with 2 surfaces right there. Your control tolerance is right there for this profile, yeah. We can identify with this profile symbol right there. And of course, this is your size and the tolerance. Again, we're dealing with the 2 surfaces, and but that can be controlled as a single surface, yeah, because it's a cold plane anyway. Here, yeah, pointing this surface, okay, 2 surface, but treating as a cold plane because they're sharing it. Here we go. When we do the inspection, of course, we're gonna bring our zones as always. So we see the yellow as a zone, and your true surface right here is right there, okay, where you are gonna apply that tolerance for that profile. We do the same thing here. I forgot to show you the size of that, yeah. So you subtract this from here, and you're gonna get this. Exaggerated. See like how this is closer, yeah, to the one side of your tolerance zone, and this one is closer to the other side of the tolerance zone in your inspection. That's kind of off. So your profile control is going to allow the full range, yeah, of size variation on the height of that part, but it's going to keep both feature surface, yeah, parallel and uniform in straightness, your flatness, and also your coplanarity. Coplanarity meaning the surfaces is sharing, yeah, the same, as a control. Okay. Now let's put them all together, and you can be able to see here your profile control tolerance zone, and then you have 2 surfaces right there, and here is your size and location of the tolerance, okay. Of course, these are going to be your 0.005, okay, is here the zone, and then of course the other one is going to subtract, yeah, for 1.188, and then going plus or minus 0.020. which is your yellow zone right there. Yeah, the size of that. So your data control reference is right here. So when you do the verification, that's where you will look at the parallelism, yeah, for the top surface with your two control surfaces right here, because they are parallel anyway. So don't forget to these little things like that. But to simplify, the whole thing is it's got to be in your tolerance zone. That's all. Yeah, it doesn't matter what it can't go outside of it. As long as you're in, then you're safe. And we repeat that with many different examples and different tolerances. Yeah. Okay, your datum plane A. We'll look at the surface. Here is a control frame for the two surfaces. So we have coplanarity. And here the size is still 1.18 because in the same part, we are in the same example, yeah? So when you think about it, now that surface is going to be far away from your datum plane A, yeah, then 1.1905, or you can minus, yeah, out of it, so 1.1855. So you add it or you subtract it, okay? Okay, now we're going to deal with the two surfaces without your geometric, yeah, tolerance. So in that case, if the origin of that height dimension, okay, here is your height dimension, if that is going to tie to the top surface, then your tolerance is reduced half, the same thing, okay? And the outcome is going to be about the same as your profile specification, because we don't have that geometric tolerance. There is no control frame given to you. So we just deal with this, yeah? Basic tolerance given to you here. So the two bottom surfaces will have to be parallel to the top surface, as well as will have to be parallel to one another, flat, coplanar within that tolerance, yeah, 0.005. Okay, then we'll get into another one. So we'll draw it like this, okay, and here just showing you the same thing right there. Your interpretation, we're going to exaggerate it, and we can see the surface imperfection right there. We can see our zone right here. Tolerance is 0.005 right here, yeah. And of course, this you're gonna divide it by 2, so you get 0.0025 on each side, yeah, of this size, which is 1.188. That's you can be able to immediately read it, yes. So if I give you this, you should be able to go back to here. If I give you that, you should be able to go into there, okay? All right. Your benefits, of course, profile can be applied. You can apply the profile to control, yeah, two or more non-continuous planar surfaces in a single plane. That's why we call it coplanar surfaces. And you can do it simultaneous, yeah, single plane flatness, your straightness, your parallelism. They all control these multiple surfaces, because for parallel you need two surfaces. Straightness, we also look at it. Flatness, we also look at simultaneously for the coplanar surfaces. Iterate the same thing, your bilateral, okay, equally distributed. And if you are dealing with the unequal distribution, then you're going to have your unilateral. So by doing like that, you can be able to verify your parallelism, straightness, flatness, form, coplanarity across the control surfaces. Yeah, surfaces are being controlled because don't you ever forget that you are manufacturing them. So if you don't control with the tolerance or value, your manufacturing is going to go crazy. So therefore, we have to keep, all right, because you are producing billions and billions parts of the same design, yeah. So even though you're using the same machine, it will get exhausted, of course, over time making the same thing. So you do have the offset, yeah, from the true sides. So anyway, so profile geometry. So don't forget the common sense, what's going on outside, while we are like so much into study like this. You need to connect to the real thing outside. So profile geometry tolerances, you're gonna require a data reference, yeah. So that's what's going on. Like language is really bulky when you have to identify it, and we gotta call many different names in order for us to be able to show that outside. If you talk about it, oh, this suffix gotta get that value like that, yeah. But when you write it, of course, we have to go into details to describe each one of them, yeah. So that's why the terms are like confusing you. Okay, so another part, we have two suffixes again, yeah? And you have your datum features. Of course, your datum features right here, yeah? And in this control frame, you can see it and see like they're tied together. Yeah, ABES. Don't forget it, the A-B mean this tolerance applied to both of them, because we combine them, yeah? Combine them all together. So you provide tolerance for your datum features has been described, in this case it's a unilateral, yeah. So you, in this example, its description is right here, so inside of the planar true profile. So let's take a look at that. So we draw, yeah, and here of course unilateral, so you have only one line, yeah. Now we have gauge right there, yeah, simulated datum A and A pi to B, which is combined anyway, and that's the tolerance is right here for two surfaces right there. Your two surfaces is right here on that plane right there, okay. So that's your bilateral tolerance, both sides. Unilateral is going to be 0.03 and bi is 0.6, okay, and we are looking at it. So if that's a bi is from here to here, let's go with your 0.06. This is unilateral, so you see only one line, you know, on this section and that section, that's 0.03. So you have two different tolerancing for this section, that section, and then the middle section, two lines, yeah, one line unilateral, two lines bi, and then one line unilateral going different profile right there. And that's what we call it profiling. You are like tracing the outline of that, okay, in this view. Don't forget the view. Okay, your variance is going to happen your datum features. Your datum is A-B, yeah, the green line right there. And then it's got to, of course, adjust to your bilateral and the unilateral, because it's controlling the internal taps, yeah, within that respective bilateral tolerance with reference to the datum A-B. Tied, by the way. So anyways, let's go into this profile, and where you can see 0.03, you have four surfaces. So if you're dealing with the four surfaces to be in the same plane, first what you have to do is you're going to see your internal tap, so here, 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 and your same surfaces right there, and we know that we are dealing with the unilateral, yeah, surface, because that's going to avoid any possibility of well, this is just telling you that you got to be careful with these internet tabs when you deal with the four surfaces, okay. They're just writing it in a very difficult way. So when you get into the variation, we will have to come into the zone. So this is your simulated datum, yeah, and then here is your unilateral, yeah, you can see that right there, and your unilateral tolerance is defined to you here 0.03, and you're dealing with the two datum tied together, yeah. So datum plane A and B at the same time for four surfaces in this case. Okay, then we'll get into the profile all around and all over after we deal with the individual stuff and different surfaces. So profile, you can use it, right, to control all surfaces. For irregular feature like outside, that would be like machine pocket or cutout, things like that, yeah. That can happen around your true profile or outline. So when you think about the blanket, yeah, control, then we're going to look at the tolerance zone, which is going to be extend over the entire part. So when we talk about this here, you can't be able to see it. So let's just go straight into the diagram so you can see a little bit better. So here is our part. see it like this, yeah, from here. So we have all the basic dimension right there. Of course, this is our control frame controlling right here, this profile, yeah. And of course, we're gonna go to the different views so you can be able to see the data, yeah, which is your primary data reference right there. Then we'll go into our zone, which is your point 4 right here for this profile. Your profile is changing like that, yeah. If you look at it from the side view, we can be able to see this right there. And then this, of course, right here. The rest of them are inside. All right. And then we will go into the exaggerated for your true profile, which still is in the zone, so we're safe. Yeah, everything is fine because your surface element is residing between the two uniform boundaries. Yeah, and of course, when you look at it from the datum reference, we know that that's got to be perpendicular to that, and it has to be within 0.4 tolerance. Okay, so now let's go into maximum radii and how we deal with that. So in this example, we can see two views right here as always, and here we have a section, okay, section unilateral surface, which is your profile, of course, right here, and it is controlled by this 0.6 tolerance with reference to the datum plane A right there, okay. Datum plane A can be seen only on the right side, based on this example. Of course, we have the size shown from here to here is you can vary between 14.0 to 14.2 in that zone. And I have, of course, a 2, okay? This is just showing you, because of the limited space that we use like a zigzag, okay? A leader line right there showing you this is going to be, your arc is going to be 2, yeah? This side and that side, it's a 58, yeah? Radius for that, because this radius is pretty, because the arc is, look at how it's shaped. Yeah, it looks like a little pointed instead of a circle like that. So your center of the arc got to be really far away. Yeah, because of the shape of that arc is not it's not circular. Yeah, it's kind of like a little chunk of your arc. So we know that the center must be so far away. So we're gonna pull it because we have a limited space to draw on this, on this space. So we're gonna draw it here with a zigzag line to show that center is 58, okay, millimeters far away. So that's a big distance. So your corners, all of them got to be, radius is 0.2 is your maximum. All right, now we're gonna zone it as always. So when you zone it, we can see the true profile right there, in that zone, of course. And then, of course, when you look at it from the side, we can be able to see these lines in that way, okay? And your center is right here for that, okay? Cylinder right there, which is this on the side view, which is looks like a groove, a dish like going into there, and that one is a ditch going into there on this view. But here, when you look at it from the side, you can see like a hollow thing, cut hollow thing. Exaggerated view, okay? I'm trying to show you again. I forgot to show you here. So when we go back to here, we see this. We come into exaggerated. I show you this already. That's a 14.2, 14.0, yeah? And you can vary in between that zone 2 lines, yellow lines. I forgot to show you this a little surface right there for this, okay? But anyway, they're accepted because the true profile is still within the tolerance zone. Now we get into no maximum radius control. And this I have already shown you in a previous example. Your R is going to be 58 millimeters, yeah? Because your center is so far away from this arc. So we have limited space, so we just bring it closer to that and show you. And of course our tolerance here for this side view, your datum plane is right there, yeah? At least you have to know. And then of course we get back into our exaggerated view, telling you, showing you all these zones, corresponding zones, and also your front view is going to have this true profile within this tolerance zone of 0.6, okay? All right, optical comparator outside looks like this. It's just a measurement. And here, of course, we can take a look at it. I also put this one on YouTube, yeah, for you. Right now I can't do it. Anyway, I will put that up for you, okay? We can be able to see it. So anyway, so let's take a look at your optical comparator right here. It looks like this, okay? So we use it for the verification technique. So you go in, see like how you can see very big for the profile that we can see with the human eye. Yeah, so I can play that again for you. So this is how we see inside of it. Like when you put a part like that, we can be able to see like this. It's kind of like making it real big, you know, and we call that the comparator. So you can see the thread gauges and also the surface, yeah, the surface. What am I saying? We can see the surface like that. Okay, so let's go. I give you the manual link right there, yeah, so you can go there and see it. Okay, so composite profile tolerancing. So when we go into here, you have your tolerance is going to apply to the location of a feature, and that's going to be controlled by your profile tolerance. Yeah. Sometimes you have like a very lesser critical design consideration. So in that case, we will be dealing with the actual feature form and also the orientation tolerances. So your composite profile, we call it composite because it is composite. We're dealing not only one thing but dealing a different thing. So let's take a look at, since always composite, we gotta change our feature control frame with two rows right there. So the very first one is a 0.9, and that the first tolerance is your location and orientation. All right, the other one is your size, form, perpendicularity, and we can combine that. So we call it a composite profile tolerancing. So the very first example, here you can be able to see that, and we have a larger tolerance, and then we have a smaller tolerance zone, okay, and that's going to refer to this profile right here, the feature on this part. A little bit difficult to see it. So now when you zone it, it's easier for us to see. So we see the true profile, and then your 0.9 millimeter, this one is going to be yellow one right there. Of course, a different view when you section it, so that's how you see in your datum here and datum there. And your another datum is right over here. Okay, now we'll get into another zone, which is your little green one right there. See? That's within this zone because it's smaller, 0.2, that's 0.9. And your 0.2 is your refined tolerance zone, which is a green. All right, then you see your actual exaggerated, but still lies within the tolerance zone, so we're okay, acceptable. Now we're going to exaggerate it, so you can see the two composite tolerance, like that in your control frame, defining the yellow one and then your green one, and then your white one is your true profile. And we have two different views to be able to see all this datum, which is A, B, and C on the coordinate process surfaces, okay? Not process, I mean surfaces. All right, now your composite profile, you can see this. I'm going to show you how your actual feature profile, okay, is going to stay within the refining tolerance zone, which is your green one. See that? And which is located right here in your another tolerance, which is a 0.9 zone, and green one is a 0.2 zone, okay? Notice, see the shift, see that shift, for your tolerance zone right there. So now it is within the larger locating zone. It doesn't affect the orientation of your actual feature profile, so it's still very safe, And your, of course, your perpendicularity got to be relative to your datum surface A. All right, now we're gonna adjust it. See like how it's different from the first one. See how it goes. So you gotta play the slide like that to see that movement. So adjustment of that refined tolerance zone is going to be maybe rotational, within the larger locating zone. But as long as your tolerance zone, as long as neither tolerance zone is violated, then it is acceptable. So we'll go into profile tolerancing your planar and conical surfaces. Okay, so let's take a look at these surfaces. So your profile controls may be used, right, to relate your feature orientation, also dimensional relationships to your dimensional reference frame. So your profile controls may also be used to control the form and also orientation of your conical surfaces. Yeah, so let's take a look at it in our first example. So here we have an example of how you can see the profile can be used to control, yeah, the surface elements. So here we have our first profile tolerance zone is 0.4 and the other one is 0.2. Okay, here just make sure that you take a look at where it is attaching, yeah, so you know like which profile the zones are, the tolerance zones are defining. So right here we have a two datum which is tie A and B, yeah, in order for us to deal with this profile. Of course, this one we're going to use A, B, and then C, which is here, because that tolerance is going to cover, yeah, from here all the way to here. Okay, and then we're going to bring in, yeah, so establish our datum. So we're going to bring our simulated surfaces right there. And your profile is a 0.4, A, B, and then C. Your profile is 0.2, A, B, and then C. Yeah, your surfaces are right there. So your datum reference, a little bit difficult to see it. So, but when you zone it, it's easier. Yeah. So when you go here, you can see now everything's a white line. Now we zone it, so you can see to clear, yeah, and zone for these control frame right there, 0.2, 0.4, true profile and true profile, the white lines. All right, we're gonna get into application. Flowchart. First, you're going to see the control applied to the surface or not. If yes, we're going to see whether that's applied to an appropriate view or not. If yes, we're going to take a look at, yeah, profile is from your basic dimension or not. If that's yes, we look at the modifier, we don't need it. If that's no, we're going to look at the basic locating dimensions, originate at your controlling datum. If that is yes, acceptable, yeah, control. We're going to see again control applied to the surface or not. If not, we're not going to accept it, because when you apply the profile to the surface, your specification got to be made, yeah, in an edge view. Otherwise, you cannot accept it. And then we're going to decide whether you have this, you know, okay, this profile of a surface that's applied in appropriate view or not. Yeah, where your true profile can be able to see clearly. If not, you can't accept it. Then we will take a look at your true profile. Got to be always be defined with your basic dimension. If not, don't accept it. Then we will look at the modifier. So your profile tolerance is always applied regardless of feature type. I've been reading this again and again for you. And if that yes, yeah, and acceptable. If that's no, we're going to check another one and look at the basic dimension. So if the basic dimensions are used to locate the true profile of a surface, then they must be originated at the source, yeah, datum. If that's no, don't accept it. If that's yes, you're going to accept it, okay? So make sure you go slow, and you might want to spend about 30 minutes to be able to get this. All right, now let's get into the summary. So we're going to take a look at our profile, and we see your line profile and then your surface, yeah, profile right there. So profile, the symbol for line profile, you don't need the base. Yeah, for surface profile plane, you need the base. So profile got to be only applied to a feature. Then profile of a line does not affect the virtual condition. Your profile of a surface may affect your virtual condition. We're going to identify each one of them here with the legend 1, 2, and 3. So let's take a look at it. Then you will look at your modifier. If the modifiers are not applicable with profile controls, we are going to get into the datum reference. Yeah, so yeah, if your datum references may or may not be used in the feature control frame. So we have two things going on. One thing is if your design requirement may mandate the use of the datum or not. The other one is your profile tolerance, yeah, or the only geometric tolerance that may or may not use the data. So basically, we just look at them, yeah, each one of them, and make sure that you address all of that when you deal with your profile. We have two, line and the surface. Yeah, line go that way. For surface, go this way. All right, so that's your profile control summary. Then you will get into your problem 81, yeah, which is your work, your homework. 81, 82, 83, 84, yeah. So you have 4 problems. So out of 4 problems, take 3 of them and submit it for your assignment requirement, and then please study, yeah. So this is going to appear in your final exam portion of it, just like that, yeah. You definitely need to get it. If you're not taking the lecture, I don't know, I tell you all the time, yeah. So those who are actually taking the lecture know what to study, and they have no problem, yeah, taking the test. Okay, well, that's it for chapter 10. So we will move into chapter 11.